Hello, stats class. For those of you who want a little extra math, I'm going to show you the derivation of the slope formula and why it makes sense. So, like I said, this is an optional video. Watch it if you're interested. Given we have a set of data in ordered pairs, x comma y, and we want to minimize the sum of the squared residuals. That's a lot to write out, so I'll tell you the abbreviation for that. SSR is the sum of squared residuals. We want to minimize that. We want to make it as small as possible, and that's what I'm going to show you how to do. And I'm going to tell you that it actually works just as well to divide this by something and then minimize it. So it's a little bit easier if we talk about minimizing the MSR, which is the mean of the squared residuals, which is the SSR divided by n minus 1. It's kind of like an average of the sum of all those squared residuals, which remember are y minus y hat squared, except we're now going to divide it by n minus 1. I'm going to take that formula and try to minimize that value. All right, so the first thing you need to know is, well, actually the first thing is it's easier if you minimize that. Second thing is it's also easier if you convert it to z-scores. So we've been working with z-scores a lot. Let's convert to z-scores because then we can work with that and then we'll convert back at the end. And so if I convert to z-scores, then there are some things that I know about z-scores that might help me. So I'm going to write down a little list off to the side here of things that I know about z-scores. For instance, I know that the mean of all the z-scores, mean zx value is 0. I know that the mean of zy is also 0, because means of z-scores are always 0. That'll make my calculations easier. My standard deviation of x or of z, no matter whether it's x or y, is 1, and that's for zx and also for zy, which is also 1. And I want to point out that that standard deviation is based on that formula that we learned before, that if I take the sum of the squares of all my z values, well, really what it is the z values minus the mean, which is 0 anyway, and divide by n minus 1 and square root it. That whole thing comes out to equal 1, which means that I could take off the square root. I could square both sides and get the variance, which is the sum of the z squares over n minus 1 without the square root. That also equals 1, and it doesn't matter if I'm talking about zx or zy. So all of that's going to make my calculations easier if I know those things. It also might help to remember that the formula for the correlation is based on z-scores. So zx, zy over n minus 1 added up is basically called r. So that may show up in my calculation somewhere, and if it does, I'm going to replace it with an r. So I'm converting my values to z-scores. That gives me a new point of means, which, remember, the point of means, x bar, y bar, the line has to pass through that point. And if I convert to z-scores, that point becomes 0, 0. Well, that's kind of convenient. I have now a line of best fit that passes through 0, 0 on the z-axes. If I make my axes into zx and zy, I'm talking about a line that goes through 0, 0, might be positive or negative, but I'll draw it positive. And that means that my slope that I'm looking for is more important than the y-intercept. The y-intercept is 0 now. That's why one of the reasons I converted to z-scores. So let's call the slope m, because you're used to working with m. So if I go over 1 and up m, I'll land on the line of best fit. So I'm going to try to find m, trying to derive a formula for m, which is the slope of the line. I'm calling it m on purpose and not b, and I'll tell you why in a little while, because there's going to be something else that's called b. So I have my zy hat, which is my estimated value for zy on the line, is just equal to the slope times zx. That's my equation, and I'm trying to find m to make this minimize what I said it would minimize. Okay. So now I want to minimize this thing, except remember this thing got changed because now I'm converting to z-scores. So this MSR got converted to z-scores. The converted version of it looks like this. It is the zy minus zy hat squared over n minus 1. So I'm going to try to minimize this, and whatever I get will give me the best possible m value. So let's do some simplifying of this thing. I want to remind you that z hat y is just m times zx. Let's replace that. So zy minus mzx squared over n minus 1. And now I'm going to do some algebra. So algebra, this is a thing that's being squared. If I'm adding them all up, it doesn't matter because I still could square this binomial right here. So I'm going to do what I've done before with binomials and multiply this out. And it's still going to be added up and divided by n minus 1, but that's fine. I'm going to do zy squared. Remember, you can't just do this squared and this squared. You have to do the whole FOIL thing. And so when you do FOIL, you get two of these guys multiplied together. So minus 2m zx zy, and then plus, oh, I forgot the m. There's an m there. And then this thing squared, so m squared zx squared. That whole thing is what you get when you multiply that out. And if you forgot how to do that, you might need to draw a little box over to the side and do zy and mzx negative. If you need this, do it. Or, you know, just watch me and trust me that that worked. When I'm adding up a whole bunch of stuff, if I'm adding up this thing plus another of this thing plus another of this thing for each point on the graph, that's the same as adding up all these and then adding up all these and then adding up all these. So I'm going to separate that out and say now I have zy squared, and I could divide them separately. By the way, the 2m is the same for every single one of them, so I'm going to pull out the 2m outside of my sum. And I'm going to pull out the m squared also because it would be times every single one of those. These are a whole lot of different things for each data value, but m is always the same. I still haven't found what m is, but that's okay. So now I'm looking at this equation going, this looks messy, but there are some things that could help me with this. Look at this thing right here. What is this? This is taking all the z's and squaring them and adding them up and dividing by n minus 1. That's this thing over here. We just said that was the variance or the standard deviation squared of all the z values, and it happens to equal 1 because they're z's. So I'm going to replace this piece with 1. Isn't that convenient? I think that's wonderful. How about this piece? This looks kind of familiar to me. I'm looking at this going zx, zy, add them up, divide by n minus 1. What is that? We've seen that before. That's the correlation. That's r. So I'm going to say this is minus 2mr. Boy, this got a lot easier, didn't it? All of a sudden, plus, what's this piece? Okay, well, this piece is zx squared over n minus 1. That's the same thing as this, except with x instead of y. It's the variance or standard deviation squared of all the zx's, which is 1. So it's kind of like a wow moment. This piece is 1, this piece is 1, this piece is the correlation. What's left here is just m squared. That actually looks really nice and simplified. All of this adding stuff up and all of that went away when I realized that I knew some things about z that would help me. So this is a quadratic equation. Remind you of some algebra stuff. This is a quadratic equation. What shape do you get when you graph a quadratic equation? I hope that you would be able to answer this if we did this in class. You get a parabola. I'm trying to minimize this parabola, or in other words, I'm trying to find the m value that makes this whole thing as small as possible. And that means I'm trying to find this point right here that is called the vertex, the minimum value. So I'm going to use what I remember from algebra to find the minimum value. And remember, if you have like I'm going to rewrite it so that m squared is first, minus 2mr. Actually, maybe the r should come before the m. Does it matter? No, except that this is kind of like x. And so I wanted to point out that if you have x squared plus something, x plus something, or that's a plus 1, you know, I hope you already know how to find that minimum value. So remember ax squared plus bx plus c, And to find the minimum, you do something like x equals negative b over 2a. Or, if you know calculus, you could do it that way, but I'm going to go with the algebra method. This is the reason I didn't want to call the slope b, because I have a b here, and it's not the same as this m. It's technically b is negative 2r. So I'm going to do negative b over 2a and find the minimum. At m equals negative b would be negative 2r over 2a, which is 2 times 1. Right? So there's my b and my a from this formula. And I can simplify this. The negatives cancel, the 2's cancel. It equals r. That's amazing. That means that if I have converted to z-scores, since I converted to z-scores, the minimum value for the slope is r. Correlation is equal to the best slope value when I'm dealing with z-scores. Okay, so that's if I'm working with z-scores. Back to here, m equals r. Nice. Now I'm going to convert back. Convert back to x and y values. So now I'm going to go, my graph now looks like this with x and y. I have my x bar and my y bar, and it's going through that point, and it's going like this. And I need to figure out the slope that works for that. And remember that the slope is just, if you go over 1, you go up r or m or whatever you want to call it. You go over 1 and up the slope. Over here, you go over 1 unit and up whatever the slope is times 1 unit. And remember that the units over here, this 1 for z, is the standard deviation. It's not the standard deviation of z, actually. Well, technically it is, but going over 1 on the zx is the same as going over a standard deviation on the x-axis. So this going over 1 is the same as going over 1 standard deviation. Going up 1, or actually going up r, is the same as going up r times the standard deviation of y. And so that means my new slope, which is m still, is now r times sy, that's the rise, over sx. I'm going over 1 standard deviation and up 1 standard deviation times r. And that r came from what I did up above. That is the official formula for the slope of the best fit line. And remember, the best fit line is the line that minimizes this messiness, or before we convert it, it minimizes this. It makes the sum of the squared residuals, whether you divide it or not, as small as possible. And the only reason I divided it, honestly, is so that when I got to this step, I would recognize these 3 things and say, oh, look, that's just the variance, and that's just the correlation. So that's the reason I'm divided by that number. Dividing did not change what the minimum was. So that's basically what's happening here. That's the slope of the best fit line. That is the derivation of why that slope works. Bonus material at the very end. You also can do one more thing with this, and that is look at that parabola again. And that vertex has a x value of r, but then the y value would be, how small can they get? Like this sum of squared residuals, how small can I make it? So this is the last little bonus piece. How small can the mean squared residuals get? And that would be the y value of my parabola. So I'm going to go back to my parabola equation, which is 1 minus 2mr plus m squared. And if I take this m equals r and plug in r for m, basically, if you found x, which is what I did, then you would plug in x to find y. That's what I'm about to do. So I would plug in, instead of putting m, I want to put r. So that's 2r squared, and that's r squared. And then I'm going to simplify. Minus 2r squared plus r squared, that's 1 minus r squared. So before I drew the line, I had just this y bar thing, right? I had a variance of 1. I had a variance of 1, which is the variation in my y values, or my zy values, right? The variation used to be 1. So we're still back in z's, I guess. Variation in zy was 1, or you could think of it as 100%. And then when I did the line of fit to minimize that, I wound up with 1 minus r squared. With the line, it's 1 minus r squared. What does that mean? We had 100% variation, and we reduced the variation, or the unpredicted variation, I should say. We reduced it to 1 minus r squared. 1 minus r squared is the unexplained piece of the variation. So that means that r squared is the explained piece. And that is in lesson 3.2c, which you may or may not have listened to that video yet, but the explained variation, we're going to talk about that in that video. So r squared is the explained variation. One more bonus thing is that because r squared is being subtracted from 1, and you can't have negative variation, right? That means r squared has to be less than or equal to 1 for this to work. And that means that r has to be between 1 and negative 1. And doesn't that sound familiar? We talked about that, and this is the reason why. This is the proof of why that happens. That r squared is the percent of the variation explained by the line, and it has to be less than 100%. Technically, it has to be more than 0 also, but the point is that means r itself is between 1 and negative 1. I'm going to save this also. So those are kind of bonus pieces that are not the derivation of slope, but they're the explanation of why this r squared interpretation is like it is in lesson 3.2c. So lesson 3.2b, I taught you this formula, and I didn't tell you why. This is the reason why. And then in lesson 3.2c, I taught you this, and again, I didn't tell you why. Or maybe you haven't listened to that second one yet, and that's fine. But there you go. There is the derivation of the slope formula and a little bit about r squared. Hope you enjoyed it.